So in this video, we continue an investigation of quantum numbers and look more closely at the magnetic quantum number. We've learned previously that the orbital angular momentum quantum number, symbol L, and the magnetic quantum number, m sub L, are definitely related, both describing aspects of the orbital angular momentum. But why is the magnetic one called the magnetic, and what does it have to do with the orientation? So previously, we came to understand that in our quantum mechanical description, the orbital angular momentum was quantized, and there were two different constraints. There were allowed values on the total orbital angular momentum, and then also quantized values with respect to the angular momentum along the z-axis. Within this figure right here, we would see how the measured values would correspond to various classical orbits in which we had a particle in motion that was tilted with respect to this xy plane. But when we think about this quantum mechanically, we want to bear in mind these are not the literal trajectories. Electrons are not moving in these classical orbits. The electrons would have measured angular momentum values as if they were in these classical orbits. So it would match that particular property, but it doesn't have the same explanation. So we're drawing an analogy the best that we can between the classical description and the quantum mechanical one. We're calling that an analogy. It's a comparison in which the things that are being compared are quite different from each other. So we can move from a classical description of angular momentum, seeing that it was also quantized within Bohr's model, and now it's once again quantized within our quantum mechanical model, but we have two different quantum numbers describing it, L and m sub L. The property itself would be the orbital angular momentum. There's a classical explanation, which were these particular orbits, and we're drawing an analogy then to try to understand it quantum mechanically. The property is something we measure, and we're trying to make sense of an explanation, recognizing that that explanation will not be the same literal one that's being used classically. So let's turn to consider, well, how do we measure this particular property? So I like this description here on the Chemistry LibreText website, where it's looking at a description of the angular momentum. So first of all, if we're describing this with respect to some axes, like the z-axis, we need to be able to physically define an axis in space. A magnet has a direction. We have a north and south, so we're going to use a magnet to be able to specify a direction for the axes in space. And we're going to see how an electron, charged particle, it's in motion, and we'll see that associated with that motion of a charged particle moving, we're going to generate electric current, and that would lead to an associated magnetic field. Key thing within here is that the magnitude of this magnetic field is related to the angular momentum of the electron's motion. So the idea is what we're going to be measuring would be an aspect of the magnetic property of the electron, and by that we'll have insights into the angular momentum. So we see within our description right here, the magnetic moment is related to our quantum number L. This would be a setup describing the particular experiment. Once again, we'll have a source of our particular atoms, send it through an evacuated chamber. Here's our magnetic field, north and south, detector on this side. Once again, the plan, the reason that we're placing it in a magnetic field, that's going to give us a direction in space. That gives us a z-axis that we can then make comparisons with. So this box is describing the rationale. The second portion right here is describing the experiment. So if we were to have our source of atoms being directed towards the detector, if we had no magnetic field, they would go right through and strike in the center. What if we turned the magnetic field on? Well, in the classic description, we would have a continuous value of the angular momentum values for the atoms, randomly arranged. So when they strike the detector, we'd have a continuous range of values. How about the actual experiment? With the actual experiment, we don't find a continuous range. Within the actual experiment, we see discrete regions where the atoms are striking the detector. As the author notes, the startling results of this experiment can only be explained if we assume that while in the magnetic field, each atomic magnet could only have one of three possible orientations with respect to the field. So it's viewing now the atoms as having a north pole, a south pole. As they're traveling through, they only strike they're deflected, and we only have three different regions where they could strike that was based on their orientation. What we're seeing is that by placing the electrons in this magnetic field, the energy levels are no longer degenerate based on the m sub L values. By placing it in a magnetic field, different m sub L values, which after all corresponded to the projection along the z-axis, we saw that there were three different allowed values, and that's what shows up within the experiment. This idea of removing the degeneracy by placing based on m sub L values, by placing the sample in a magnetic field, that also shows up with what's called the Zeeman effect. So this would be where we're looking at the different emission spectra. In the absence of a magnetic field, we know that the lines only depend on the principal quantum number n. However, if you repeat the experiment and you have an external magnetic field, you find that lines are split. So instead of having a single transition based on n, you see three different ones if you're looking, in this case, for the hydrogen atom. We're seeing here a splitting or a removal of the degeneracy of the magnetic quantum number. So in the absence of the field, we'd place them all on the same energy level. When we have the field present, we see the splitting out of them. That is occurring for when we had m sub L ranging from -1 to +1, or from -2 to +2. This is from the Hyperphysics website. They also do a nice job of explaining what are called selection rules for these electronic transitions. So you notice within here we have quite a few different lines, and if you were to draw all the possible lines between this top set and the bottom, you'd have even more. When we're looking at spectroscopy, oftentimes there's constraints on what kinds of transitions are possible, and different selection rules are appropriate for different forms of spectroscopy. In this case, we see the selection rules, or the conditions that have to be met when we're looking at these electronic transitions. If we look at the ones that then take place, even though we have a lot of lines, all three of these are equal to each other. All three of these are equivalent. All three of these. So even though within this picture there's 9 different transitions shown, we only end up with 3 spectral lines. This is something that turns out you can explore a little bit within the PhET-Sim. So the PhET-Sim models of the hydrogen atom, when we're looking at the energy levels, you've probably noticed before that we have n equals 1, 2, 3, but there's also m values shown, and also the corresponding L value. So if we go to the PhET-Sim, if we look at the possible energy levels, for the Bohr model, we only have n. The Schrodinger model, we have different L values, and then depending on the transition, it may also designate what the m value would be. So I'm sending less than white light through, and we have the different photons being emitted. So if you track through within this, the PhET-Sim is consistent with these particular selection rules. It reflects those. So we might have an emission when we go from 2 to 1. Notice that the L value is changing. It went from L equals 1 to L equals 0. We have a 2p going to a 1s. Here's another example consistent with the selection rules. So the FET designers, they know the selection rules, and that's included within their setup here. One thing that I want to point out that's novel is this particular set. So you can have a emission in which the electron goes and finishes in a 2s. Nothing violating the rules with that. But if it's in that particular one, can it then go straight from a 2s to a 1s? Or is that in violation of the selection rules? 2s to 1s, we're not seeing a change of +1 or -1 for the L value, so it can't happen. So if it's in a 2s, the only spot it could move to next then would be back to an excited state and then subsequently return to the ground state from there. I'm pointing that out just because I set up once within my class a demonstration like this. I was looking at sending in specific wavelengths, photons with specific energy, and I was trying to illustrate what would happen if I was looking at the transition from 1 to 3. So that's at 103 nanometers. So within here, you can choose a particular value. I'm going to send in photons with 103 nanometers. What happened there was it went from n equals 1 to n equals 3. When it relaxed, when it came back down, it went to this 2s. And notice what happens. It's trapped there. It's being described as an excited atom. It can't move back down to the ground state because that would involve a change of L of 0. That's not allowed. It can't move to an excited state because all the photons here corresponds for 1 equals the transition from 1 to 3, and that doesn't match up with any of these subsequent ones. Any thoughts on how we can get out of this dilemma? Let's go back to sending white light through. So that had a photon it absorbed and the excited state came right back down. We're going to need it to go to an excited state and then return back to the ground state. Just pointing out that the FET-Sim, they have it right, and one has to be careful when they're setting this up. If you're using it as a demonstration, that you don't run afoul with the particular selection rules. So this is called the Zeeman effect. One other idea related to this is what's called the anomalous Zeeman effect. So we have this description here for the normal Zeeman effect. The splitting as we remove the degeneracy of the M sub L values when we have it placed in a magnetic field. This is the normal Zeeman effect. However, as described here, there's other examples in which the splitting is not 1 to 3, but into 4, 6, or even more bizarre arrangements. This is what's called the anomalous Zeeman effect, and was very puzzling to the researchers of this era. Several of the historical readings share Pauli's perspective. It was remarked here in 1922 that as he was out and about, he looked unhappy. Pauli's response: how can one look happy when he's thinking about the anomalous Zeeman effect? I don't know why. I like the quote. And the anomalous Zeeman effect then would look something like this. Instead of having the line go from 1 to 3, we have far more complex patterns. What explains these far more complex patterns is the spin. Within here, it says the anomalous one, when an electron spin is included, there's a greater variety of the splitting patterns. That wasn't present in the normal, but it is in the anomalous one. Spin, that's our last quantum number that we're interested in. The last quantum number that we will seek to investigate. And that investigation must somehow also include a magnetic feature. That's what we'll talk about in another video.